Some dynamic programming subproblems use constraints like including the last element, or checking that xi is equal to yj. These same problems usually require taking the max over the table, rather than just using the last entry in the table. So a common question students have is when the subproblems need to be including the last element, and when you're going to be needing to taking the max over the table, rather than simply using the last entry. The bad news is that dynamic programming requires intuition to solve novel problems. It's usually not going to be sufficient to rote learn different solutions and expect to apply them as is. Needing intuition means that you're going to need to practice a lot of problems, and sometimes struggle through them. When you do this, you'll learn different techniques that can be applied and start to get a feel of when you need to apply them. So in this video, we're going to look at a problem known as the longest increasing subsequence problem, and try to build intuition around when we need to be including the last element, and when we have to take the maximum over the table. In the longest increasing subsequence problem, we have a set of input numbers, and want to find the length of the longest increasing subsequence within the input. Subsequence means the numbers don't have to be contiguous, which means we can skip elements. For example, with 1, 2, 1, 3, 2, the longest increasing subsequence is going to be 1, 2, and 3. When we first try to formulate a subproblem for a dynamic programming problem, we're going to try taking a direct prefix of the problem, as that is generally going to be the simplest approach. For example, if we have L is equal to the longest increasing subsequence in X, the subproblem might be L of I is the longest increasing subsequence in X 1 to I, which means we're only going to be considering the first I elements in X. So let's try to work through an example with this attempt at the subproblem definition. When doing this, we're going to be tracking the current longest subsequence. The new input's going to be 4, 8, 1, 2, 4, 1, and 9. So we start at 4, and at this point, the longest subsequence is obviously going to be 1. Next we move to 8. 8's greater than 4, so we're going to have a longest subsequence of 2 here. Next at 1, 1 is less than both 4 and 8. In this one, it's going to be a kind of start of a new subsequence, so the current longest subsequence is still going to be 2. When we get to 2, we get an interesting problem here. We now kind of have two candidate sub-solutions here. So we've got 4 and 8 of length 2, and we also have 1 and 2 of length 2. So the current longest subsequence is still going to be 2. But things get really interesting when we get to 4. With 4, there's kind of a cutover from the original solution with 4 and 8 to a new solution involving 1, 2, and 4. So our longest subsequence is actually going to be of length 3 with 1, 2, and 4. Next, we have an input of 1. This isn't involved in any of those subsequences, so the current longest subsequence is still going to be 3. And next we have 9. 9 could be involved in either 4, 8, and 9, or 1, 2, 4, and 9. So the current longest subsequence is of length 4. So what we saw with that second 4 poses a bit of a challenge for creating a recurrence relation to actually solve this subproblem, in terms of, the earlier subproblems, as we kind of have this abrupt cutover in the possible solutions mid-sequence. Our optimal sequence is 1, 2, 4, and 9, but the table values for 1 and 2 are kind of keeping track of a previous subsolution, so we can't create a recurrence relation for this exact subproblem. But the subproblem definition doesn't have to be a strict prefix of the original problem, so what we're going to need to do is change our subproblem definition a bit to allow this recursive subproblem formulation. Instead, we're going to try L of I is equal to the longest increasing subsequence in x1 to I, including xi. By adding this constraint, the problem becomes recursive in nature. For each table entry, we're going to add 1 to a previous length in the table. This length is going to be whatever length is the highest, while still ensuring that xi is greater than that previous value in x. So to show you what I mean, let's work through the same problem as before. 4, like in the last example, is going to start with a length of 1. And with 8, we know we can add 8 to 4, so we end up with a length of 2 for this second entry. At 1, however, things get a bit different. 1 is the start of a new candidate solution, so its length is going to be 1. Similarly at 2, we can't append 2 to 4 and 8, so we're going to try appending it to 1, and we get a length of 2 here. The thing that's different about this one to the last example is that this 2 here, it's not ambiguous between 4 and 8 and 1 or 2. The 2 here is actually tracking 1 and 2. Next with 4, we can't append 4 to 4 and 8, but we can append it to 1 and 2. So we get a length of 3 here, which is tracking 1, 2, and 4. 1 we can't add to either of the previous candidate solutions, so we're going to start a new candidate solution of length 1 here. And finally with 9, it can be appended to either of the previous candidate solutions, but the longer one is appending it to 1, 2, and 4. So here we get a length of 4. After running through this example, the recurrence relation should be apparent. Note, however, that this modification to the subproblem came at the cost of the subproblem being a true prefix, and this affects what we need to return as the final solution if we were to write pseudocode. Imagine if we now had 4, 8, and 1 as our input. The longest subsequence would be 2 and not 1. So we're going to have to take the maximum value over the table rather than simply returning the last element in it. More generally, these patterns are usually necessary when there are multiple candidate solutions, where appending a new value can result in the optimal selection amongst the previous values to change. In that case, the subproblems have to track information about the candidate solutions rather than just the optimal solution. This usually manifests itself with the including the element at I constraint and needing to return the maximum over the table in the pseudocode. In some other problems, such as the longest common subsequence between two strings, we can accumulate a solution across the entire table instead. There can't be competing candidate solutions, as any matches can contribute to the overall solution, and doing so will improve it. So we can kind of greedily match, and we don't have to worry about tracking candidate solutions as we had to in the longest increasing subsequence problem. So in the example on the screen, we can take either the first AB or the second AB, and it's not really material to the overall answer. If it started with A, B, then we could similarly take either the first or the second A, followed by that B. Unlike in the increasing subsequence problem, our earlier choices therefore don't really affect our future choices, and we don't need to track the candidate solutions, just one overall greedy solution. If we instead wanted a substring, that is, the matching substring was contiguous, then we would care about candidate solutions again, and we would need to add that constraint back. This is why it's so important to practice problems and avoid peeking at their solutions, even if it means you need to struggle a bit with them. It's very easy to read a dynamic programming solution and see that it's correct, but it's a lot harder to build the intuition to be able to solve one from scratch. The trial and error process of solving a problem and seeing why you need to apply certain techniques is a really crucial part of learning dynamic programming. I hope you learned something from this video. If you liked it, please consider liking the video and subscribing to my channel. Thanks for watching.